So the next stage of differential equations that are slightly more complex is those that require you to separate the variables, and I'll show you what I mean. You start off with an equation such as this one, y dy by dx equals tan x, and now your dy by dx term has got a coefficient, i.e. y. To solve this, we still need to integrate. So what we're going to do is we're going to integrate both sides as we were doing before. So this side we're going to integrate with respect to x, and the right hand side we're going to integrate with respect to x. And this is where things get slightly interesting. If you recall, when we were doing implicit differentiation, we differentiated as it was with y, and then we gave it some respect, i.e. dy by dx. This is the exact opposite. We're going to integrate as if it was with y, and we're going to take away its respect, remove its dignity completely. So these two terms are going to simply go, allowing us to integrate with respect to y on this side, and yet integrate with respect to x on this side. Some would say that these two terms cancel out as a fraction. Doesn't quite work in that way if you think about it as fractions, but when you look at it mathematically, this is the end result. So you've got the integral of y dy equals the integral of tan x dx. Well, the integral of y is obviously y squared over 2. And to think about the integral of tan x, you probably want to be thinking about it being, unless you know the standard term, the integral of sine x over cos x. And what you should spot at this point is that this integral here takes the form of f dash x over f of x. Therefore we know that we can integrate it as a standard result using the Lund integrals. So this is going to be minus Lund cos x. This bit here is obviously still y squared over 2. And don't forget your constant term, c. And that is it, integrated, and we've got a solution to this equation. Moving on from there, you can have slightly more complex variations that require you to do a little bit of work first. So in this case, we've got 2x dy by dx equals y squared plus 1. And what we need to do now is have our x terms here on the right hand side and our y terms here on the left hand side. To do that, we need to multiply and divide. Adding and minusing won't unfortunately allow us to integrate effectively, so we have to do either multiplication or division. So the first thing I'm going to do is divide by 2x on both sides. So I get dy by dx equals y squared plus 1 over 2x. And now I'm going to divide by y squared plus 1 on both sides. And I get 1 over y squared plus 1 dy by dx equals 1 over 2x. This here is the separation of the variables. This is exactly what we've just done. We've just separated the variables out. We're now going to integrate with respect to x, which, if you recall what we did in the last question, allows us to cancel out this dx term here, and it's actually going to be an integral with respect to y on the left, and an integral with respect to x on the right. That leaves you with arctan y on the left, because you obviously spotted that this was an arctan result, equals a half ln x plus your constant c. So just going over that again, we decided we wanted this term over on the left, this term on the right, so we divided by both terms to swap them over to get this line here, and this is before we even integrated. Once we got this line, we then integrated with respect to x on both sides, but that cancelled this dx term, leaving us with dy, and on the right hand side we still integrate with respect to x. Do the actual integration and you end up with the solution.